Welcome to solverfy.
In this problem, we know that a buffer is prepared by mixing 204 milliliters of 0.452 molar of HCl and 0.5 liters of 0.4 molars of sodium acetate. We have two parts to this problem. A, we need to find the pH of this buffer solution. And for B, we need to know how many grams of KOH must be added to 0.5 liters of the buffer to change the pH by 0.15 units. So in this problem, we are given this information. We will first need to solve for part A. We can first find the moles of HCl. 204 milliliters is equivalent to 0.204 liters. A mole, we know that 1 molar is a mole over a liter. So we can just multiply the volume by its molarity. So we know that there are 0.0922 moles of HCl. Next, we need to find the moles of sodium acetate. We do not need to do any extra conversion because it is already in liters, and we can directly do the multiplication to find the number of moles. If we compare these two values, we can see that the number of moles for HCl is less than the number of moles for sodium acetate. So we know that HCl is the limiting reagent. It will run out first. Given this information, we can establish an ice table. We can first write our equation of the reaction. And our ice table, which stands for initial, change, and equilibrium. We have 0.092, 0.200, and 0. Because we are trying to find the pH of the buffer solution, these two are what we are considering. We do not need to consider sodium chloride. Our change, we are going to use up all of our HCl's because that is our limiting reagent. And at equilibrium, here are our values. And our total volume, as we know, we have used 204 milliliters of HCl and 0.5 liters of sodium acetate. All we need to do is do the addition. We will need to use this information to find the number of moles for the acid and the conjugate base. So we will calculate this portion. We know that 1 molarity is a mole over a liter. So, given what we know already from our calculations, given over here, and our final volume, we will do the same for the conjugate base. Which gives us 0.131 molar. Next, we will need to use the Henderson-Hasselbalch equation, which states that the pKa, the pH equals to the pKa plus the log of the acid over the conjugate base. And to solve this, we need to know the Ka value of acetic acid, which is 1.8 times 10 to the negative 5. We know that the pKa is the negative log of our Ka. And so using our given information from the appendix, we know that the pKa is 4.74. We can plug in the rest of our information into the equation to solve for the pH. And our pH is 4.81. That is our solution to part A. For part B, we can find, since we are trying to find how many grams of KOH must be added to the 0.5 liters of buffer to change the pH by 0.15 units, we can first solve for the change. So our pH is 4.81. Let's add 0.15, and after the change, our pH would be 4.96. Our total molar, which is the addition from what we have solved from part A, would be 0.284 molar. This is extended from this relationship. We will need to use this relationship later in our problem. Let's mark this as equation 1. And we can plug in our information now to the Henderson-Hasselbalch equation to find the ratio of the acid and the conjugate base. And plugging in our values into our calculator, we know that the ratio is equal to 1.644. We will need to know this relationship later. We'll mark this equation as equation 2. If we multiply both sides of equation 2 by the conjugate base, we have rearranged our equation and have expressed the acid in terms of its conjugate base. And then we can plug this equation back to our equation 1 to try to solve for our conjugate base. We can do the addition, although there are no numbers before the CH3COH, but there's a 1. So this would give us 2.644 CH3COOH, which is 0.284. We solve for this equation, and we will find ourselves with the molarity of CH3COH, which is 0.107447 molars. We can use this information and plug it back into equation 2, which is a little complicated, but here is our equation. We know the molarity or the concentration of CH3COH already. We can just plug it into our equation, which is 1.644, and we will find the concentration of the acid. Next, we can find the moles of the acid. So we can use the relationship that we know about the molarity and its volume to its moles. So if we multiply what we found by the volume, since we know that the KOH is added to 0.5 liters of the buffer, we can solve for the number of moles by doing multiplication. And we can find the initial number of moles by using information found in part A. In part A, we have found that the molarity is 0.153, and we multiply by the volume, and we find ourselves 0.077 moles. We can do the subtraction, and we can find how many moles of CH3COO is needed to be added. We can do the subtraction. We will find ourselves with 0.0117 moles of CH3COO minus. This is the amount that needs to be added. Next, we can look at the equation if we were to add KOH into the buffer. We will notice that they are all in a 1:1:1 ratio. And so, since we have 0.0117 moles of CH3COO, we will need the same amount of moles for KOH because it is in a 1:1 ratio. We can solve for the grams of KOH that needs to be added by multiplying it by the molar mass to find, this is in moles, the grams which is 0.66 grams of KOH.